Hello everyone, this is Manoj SHENDRE. Welcome to my YouTube channel. After very long, my channel name is Thermal Engineering by Manoj SHENDRE, and this channel is dedicated for the students, those who are studying in the VTU, 5th semester Mechanical Engineering. So today we are going to discuss the module number 5, that is steam turbines. In that we have one of the important derivation from your examination point of view, that is condition for maximum blade efficiency of a two-stage impulse turbine. In the previous class we studied the condition for maximum blade efficiency of a single stage impulse turbine, and single stage steam impulse turbine is also known as de-Laval turbine. In many of the competitive examinations, you can expect this question. So which of the following is the example for the single stage impulse steam turbine? The answer is de-Laval turbine. Similarly, the example for two-stage impulse steam turbine is a Retive turbine. And the example for 50% reaction turbine is Parsons turbine. Okay. So today we are going to derive one of the very important aspect related to your examination, that is condition for maximum blade efficiency of a two-stage impulse steam turbine, right? Okay. Let us understand what do you mean by the two-stage impulse turbine. As the name itself indicates, we have the two rows here in the first stage, two rows in the first stage, and the two rows in the second stage, and two rows in the second stage. In the first row, we have the set of nozzles. In the first row, we have the set of nozzles, which converts the high pressure energy of steam into high velocity jet. That means upon the drop in enthalpy, that energy is converted into high velocity jet, either kinetic energy, right? So it enters into the first set of moving blades. Right? So these two rows together constitutes one stage. These two rows together constitutes first stage, stage number 1. Similarly, the steam from the first set of moving blade, it enters into the first set of fixed blade. These are the fixed blades. These are the fixed blades. Okay. So whatever the steam which is coming out from the first set of moving blade, it carries some potential energy. Still, it carries some the pressure energy. Okay. So that pressure energy, that remaining pressure energy is converted into high velocity jet, and finally it enters into the last set of moving blades. So this is the set of nozzle. N stands for nozzle, and this is a moving blade, the row of moving blade. Next, this is a set of fixed blades. Let me use MD for moving blade and FD for fixed blade. And the last set of moving blade, we have MD again, the moving blades. Okay. So these first two rows together constitutes first stage, and the second two rows constitutes the second stage, right? So this is stage number 2. Now, how the pressure and velocity variation takes place across the four rows? So this figure indicates how the pressure and velocity varies across the four sets of moving blades. In the first set of rows, as we know that nozzle is a device which converts the potential energy into high velocity jet, right? The potential energy into high velocity jet, or upon the drop in enthalpy, the steam is converted into high velocity jet. Okay. Now let me use the dotted line. For representing the pressure, and let me use the straight line to represent the variation in velocity, right? So dotted line is for pressure variation, dotted line is for pressure variation, and the continuous straight line is for velocity variation, is for velocity variation, right? Okay, the continuous line is for variation in velocity. Now there is a drop in pressure. There is drop in pressure in the nozzle, and as it moves over the moving blades, the pressure energy remain constant. The pressure energy remain constant, right? As it moves over the moving blades. Now, when it enters into the second set of fixed blades, this is a fixed blades. After nozzle, it enters into the moving blade, then it enters into the row of fixed blade, right? So there is further drop in pressure. There is further drop in pressure. And finally, when it enters into the last set of moving blade or the second set of moving blade, the pressure will be equals to the condenser pressure. The pressure remain constant. So whatever the steam which is coming out from the last row of moving blade, it experiences the condenser pressure. This is a condenser pressure. Condenser pressure. The condenser pressure, right? Okay. Now, how the velocity variation takes place? Let us discuss how the velocity variation takes place. So we know that the nozzle is a device which converts the high pressure energy of steam into high velocity jet. The velocity of steam will increase in the first set of nozzle. The velocity from the minimum, it increases to maximum in the first set of moving blades. Upon moving into the first set of moving blade, upon flowing through the first set of moving blades, the velocity gradually reduces, and as it enters into the last set of fixed blade, this is the second set of fixed blade, velocity again increases. Velocity again increases to some extent, right? It carries some pressure energy, fine. So because of the drop in that pressure energy, the velocity of the steam will increase, right? So upon moving to the last set of moving blade, the velocity continuously decreases. Okay, so it becomes zero, almost it is zero. So practically speaking, velocity will not be zero, but to obtain the condition for maximum blade efficiency, theoretically we assume that whatever the steam which is coming out from the last set of moving blade, it experiences the zero velocity. It experiences no velocity. So to obtain the condition for maximum blade efficiency. Okay. So this is the curve for variation in velocity, and this is a curve for variation in pressure. Right. The dotted line is for pressure, and the continuous line is for velocity. Right. Now, how to draw the velocity triangle for first stage and second stage? So we have to keep it in mind that we are deriving the equation for condition for maximum blade efficiency of a two-stage impulse turbine. The condition for maximum blade efficiency. Okay. So what we have to assume? What is our primary assumption? What is our primary assumptions? We have to ignore all the type of losses. To get the condition for maximum blade efficiency, we have to ignore all the types of losses. And the second condition, uh, the losses incurred by fluid or the steam while flowing over the curved blades, because of the friction between the flowing steam and the inner surface of the blade, it is almost ignored. We have to ignore that because we are deriving the condition for maximum blade efficiency, right? And the third main assumption is the velocity which is coming out from the last set of moving blade, it is almost zero. That is, velocity of the steam which is coming out from the last set of moving blade is zero. The last important assumption is the blades are equiangular. The blades are treated to be equiangular. Say for example, I am considering the alpha 1 as the nozzle angle. Use the alpha angle for the fixed blades or the nozzles, and use beta as the angle for the moving blades. I repeat, Alpha is the angle for nozzle or the fixed blades, and beta is the angle for moving blades, right? So we are dealing with the first set of moving blades. Inlet angle is beta 1 and outlet angle is beta 2. Outlet angle is beta 2 here, right? Now similarly, for the fixed blades, we have to use the alpha, right? So alpha 1 is already known. Alpha 1 we have already taken, right? So now here let me take alpha 2. Here is alpha 3. Similarly, for the last set of moving blades, again we have to use the beta, right? So already we have used the beta 2. Now let us use beta 3 and beta 4. Beta 3 and beta 4 here. Beta 3 and beta 4. So these are the angles for fixed blades, moving blades, and the set of nozzles, right? There should not be any confusion while taking the angles, right? You should be very careful. Now let us discuss how to draw the velocity triangle, the combined velocity triangle for both the stages, right? Both the stages. Okay. So let us draw the simple flow diagram for steam, right? Let us start with the nozzle. This is a set of nozzle. These are the nozzles. Okay. Let me assume a single nozzle, right? With the angle alpha 1. With the angle alpha 1. The steam comes out from the nozzle with the velocity v1. The steam comes out of the nozzle with the velocity v1. It enters into the first set of moving blades. It enters into the first set of moving blades. These are the moving blades with the angle beta 1, beta 2 respectively. These are the moving blades. Okay, MB stands for moving blade. Beta 1 is inlet angle and beta 2 is the outlet angle, right? Next, it enters into the first set of fixed blades. These are the fixed blades. Okay, FB. FB stands for fixed blade, right? Now, as we know that for fixed blades or nozzle, we have to use the alpha. Alpha 1 is already used, alpha 2, and here it is alpha 3. Alpha 2, and here it is alpha 3. Next, it enters into the second set of moving blades. It enters into the second set of moving blades. This is the moving blade here, moving blade. And similarly, we have to use the angle as beta for the set of moving blades. So beta 3 and beta 4. Beta 3 and beta 4. Right? Okay. Now, whatever the velocity of steam which is coming out from the first set of moving blade is V2. This is V2. Okay. This is V2. Now, whatever the velocity which is coming out from the first set of moving blades and it enters into the fixed blade, the velocity almost remains same. This is V3. This is V3. This is V3. With the same velocity, it enters into the last set of moving blades. That will be V3. And here, we'll take here it as V4. V4 is the velocity of steam which is coming out from the last set of moving blades. And make sure that here the velocity of steam which is coming out from the first set of moving blade, that will be equals to velocity of steam which is coming into the first set of fixed blades. That means V2 will be equals to V3. V2 will be equals to V3 here, right? Velocity remains constant while it is moving over the moving blades. Or else you can take the same here, V3. You can take the same V3 here. Already we have taken, right? Now this is V3 same and this will be V4. And we are assuming that V4 is always 0 theoretically. Theoretically speaking, V4 is always equals to 0. It does not experience any kind of velocity while coming out from the last row of moving blades, right? This is a condition for maximum blade efficiency. Now let us try to draw the combined velocity triangle. Let us try to draw the combined velocity triangle. The first, u is constant. U represents the tangential velocity of blade. U represents the tangential velocity of blade. So we have the set of runners. Okay, we have the set of runners on the which are mounted on the same shaft. So if the speed of the or the RPM of the shaft is same, then definitely it experiences the same tangential velocity. That is, U remains constant. So remember, in case of multi-stage impulse steam turbine, U remains constant. The tangential velocity of the runner, U remain constant. Okay. So if you know the diameter of runner, if you know the RPM, then by using the formula U equals to pi dn by 60, U equals to pi dn by 60. Okay. So this is the formula to calculate the blade velocity. The blade velocity, right? Let us try to draw the inlet velocity triangle. This is the inlet velocity triangle. Okay. V1 velocity. V1 is the absolute velocity of steam at the inlet. It has three components. It has three components. First one, horizontal component, which is the tangential component or tangential velocity component or viral velocity component. Second one is the relative velocity component, VR. The third one is the flow velocity component, VF, which is vertical. Okay. So this is the relative velocity component, VR, relative velocity component, VR. The vertical component is VF. Its vertical component is VF. VF is the axial velocity or the flow velocity component. Both are same, right? Join these two. Join these two. Now let us take the angles. While taking the angle, you should be very careful. This is a base U, right? And this complete base is dedicated for VU1. VU1 stands for the tangential velocity component. U is a tangential velocity. V1 is the absolute velocity of the steam. And VU1 is the tangential velocity component. VR1 is the relative velocity component. And VF1 is the flow velocity or axial velocity component, right? So V1 experiences the angle alpha 1 with respect to horizontal. VR1 experiences the angle beta 1 with respect to horizontal, right? The complete horizontal component is VU1. Is VU1. You have to practice this, okay? You have to practice. Now this is the inlet velocity triangle for first stage. This is the inlet velocity triangle for first stage. Now how to draw the outlet velocity triangle? Start with this. Start from here. This will be VR2. This will be VR2. The relative velocity component at the outlet of first set of moving blades. And this will be absolute velocity of steam at the exit of absolute velocity of steam at the exit of first set of moving blade, right? First set of moving blade. The vertical component is VF2. Is VF. The flow velocity component at the outlet. And mark the angles. For V2, the angle is alpha 2. And for VR2, the angle is beta 2. So for V2, the angle is alpha 2. And for VR2, the angle is beta 2. Right? Now, this is the horizontal velocity component VU2. VU2 is the horizontal velocity component or viral velocity component at the outlet of first stage. Okay. Okay. Now let us name all the points here. A, B, C, D, E, and F. This is the combined velocity triangle for first set of or the first stage. Okay, this is a combined velocity triangle for stage number 1. Let us use here stage 1. Stage 1. Let's move further. How to draw the combined velocity triangle for stage number 2? This is the first stage. Let me write here. This is the stage 1. And this is the stage number 2. Stage. Right. Now let us try to draw the combined velocity triangle for second stage. Take a locus from point C and point number D on your graph paper. Take a locus from point C and point D and mark here the same. The magnitude of this vector is same. U remains constant. The tangential velocity of the blade or the tangential velocity. You can ask, sir, how we can, why we are not differentiating from the U1 and U2 separately? Because both the runners, remember, both the rotors are mounted on the same shaft, right? If the RPM of the shaft is same, if the diameter of this, both the runners are same, right? Then the peripheral velocity or the U remains same. The tangential velocity of the runner will also remain same. So that's why we are not differentiating the U1 and U2 for first stage and second stage respectively, right? U remains constant. Now for the second stage, it enters with the velocity V3. It enters with the velocity V3. Okay. In the second stage of moving blades, okay, second stage of moving blade, the V3 remains same. Right. Now it has two components. First one is inclined component VR3, and the next one is vertical component VF3. VF3. Okay. Join these 2 points. Right. Now alpha 3 is the angle for V3, and beta 3 is the angle for VR3. Beta 3 is angle for VR3. This is alpha 3 and this is beta 3. Hope this is visible, right? Okay. Now VU3 is the tangential velocity component or wiggle velocity component for this velocity triangle. Right? VU3. Similarly, how to draw the outlet velocity triangle? As we know that, as we already discussed, the velocity of steam which is coming out from the last set of moving blade, it experiences zero velocity or the minimum velocity, least velocity. When the velocity will be minimum? When it is vertical. So if you observe VF3, V3 and V3, which one is minimum? The magnitude of VF3 is minimum because it is perfectly vertical. So V4 should be perfectly vertical. That means VF4 and V4 both should be equal. In that condition, the obtained velocity, the blade efficiency will be maximum. The obtained blade efficiency will be maximum when VF4 is equals to V4. How to draw? Look at the board carefully. So this is VR4, relative velocity component, VR4. And the vertical velocity is V4 equal to VF4. V4 equals to VF4, right? This is a least velocity. V4 is a least velocity, right? And the corresponding angles are beta 3. Sorry, beta 4. So for VR4, the angle is beta 4. Now, how about the VU4 here? The wiggle velocity component or tangential velocity component at the outlet. Obviously, it will be equals to 0, right? So VU is equals to. Is that clear, guys? Okay. This is how we have to draw the combined velocity triangle for two-stage impulse turbine. Hope this is clear, right? Okay. Now let us try to derive the equation for condition for maximum blade efficiency, that is phi. First we'll obtain the phi, then we'll obtain the efficiency equation, right? Okay. Okay, look at the board carefully. Now, the sum of VU1 and VU2 that can be written as delta VU1 for first stage, delta VU1 for the first stage. It is a distance between B to E. Similarly, for second stage, it is delta VU2. Delta VU2. It is the distance from H to J. It is the distance from H to J, right? Now let us analyze. Let us obtain the expression for work obtained from the first stage and work obtained from the second stage. Then after, we'll combine those two equations to get the total work obtained from both the stages. The total work obtained from both the stages. Then after that, we'll divide that equation, that total work done equation, divided by the total energy supplied, that is kinetic energy supplied to the rotors. Okay, so with that we can get the efficiency for the blade efficiency. After that, we'll differentiate that maximum blade efficiency with respect to some parameter and equate it to 0 to get the condition for maximum blade efficiency. After getting the condition, that is the value for 5, then we'll resubstitute that value in the blade efficiency equation to get the equation for maximum blade efficiency, right? Okay. Now in the first stage, the work done W1, work done per kg of steam, in first stage, is given by W1 equals to U VU1 plus VU2, U into VU1 plus VU2 divided by GC. U VU1 plus VU2 divided by GC, right? Or this equation can also be written as U into delta VU divided by GC. Can write here delta VU. So VU1 plus VU2 is a delta VU. Okay, just in place of VU1 and VU2, we have written delta VU1 divided by GC as it is, right? Okay, now look at the board carefully. So delta VU can also be written as VR1 cos beta 1 plus VR2 cos beta 2. It can also be written as VR1 cos beta 1 plus VR2 cos beta 2. So VR1 cos beta 1 is BC, because cos, look at the right angle triangle carefully, ABC. Look at the right angle triangle ABC carefully. Cos beta 1 is BC divided by VR1. BC divided by hypotenuse. Base divided by hypotenuse, right? Or the BC can be written as VR1 cos beta 1, right? Similarly, CE can be written as VR2 cos beta 2. So W1 can also be written as this U remain as it is. U by GC remain as it is. Now delta VU can also be written as VR1 cos beta 1. VR1 cos beta 1 plus VR2 cos beta 2. VR1 cos beta 1 plus VR2 cos beta 2. Right? Okay. A little consideration shows that, as we discussed in the earlier stages, for getting the condition for maximum blade efficiency, we have to ignore all the losses, and especially frictional losses, and all the blades are symmetrical in nature. That means inlet blade angle is equals to exit blade angle. Beta 1 equals to beta 2. Alpha 1 equals to alpha 2. Beta 3 equals to beta 4. Right? VR1 equals to VR2. VR3 equals to VR4. Right? So if we assume, let VR1 is equals to VR2 and beta 1 is equals to beta 2. If we assume this, then I can write this equation as W1 equals to U by GC into 2 times. Both will become same. Okay. If we take VR1 equals to VR2, beta1 equals to beta2, then it will become 2 times VR1 cos beta1. 2 times VR1 cos beta1. VR1 cos beta1, right? Now VR1 cos beta1 can also be written as, look at the board carefully. VR1 cos beta1 is BC. This BC can also be written as BD minus CD. BD minus CD. BD is V1 cos alpha 1 and CD is U. V1 cos alpha 1 minus U. V1 cos alpha 1 minus U. So W1 equals to, let us take 2 outside the bracket, 2U by GC, 2U by GC into VR1 cos beta 1 is V1 cos alpha 1 minus U. V1 cos alpha 1 minus U. V1 cos alpha 1 minus U. So let us keep this as equation number 1. Let us keep this as equation number 1. Now similarly, while dealing with the second stage, this is a work obtained from the first stage. We have to obtain all the equations, that is equation number 1 and equation number 2 in and V in alpha. V1 alpha 1, U V1 alpha 1, right? Let us obtain the work done for the second stage in terms of again V1, U and alpha. Okay, look at the board carefully. Work done per kg of steam in second stage. Okay, we'll write it on the top so that there is a constraint for the space. There is a constraint. Okay, let us obtain the equation for work obtained from the second stage of moving blades, right? So work done per kg of steam in the second stage of moving blades. Let us take it as W2. Let us take it as W2, which is equals to U times, let us use the same equation, U by GC into delta VU2. U by GC into delta VU2. Now here, delta VU2 is, again, it can be written as VR3 cos beta 3 plus VR4 cos beta 4, right? The total length from H to J, is the sum of HI plus IJ. HI plus IJ stands for the total length from H to J, that is VR3 cos beta 3 plus VR4 cos beta 4. Let us write the same, U by GC as it is into VR3 cos beta 3, VR3 cos beta 3 plus VR4 cos beta 4. VR3 cos beta 3 plus VR4 cos beta 4. Similarly, let us assume the same thing, that is VR3 equals to VR4 as we discussed in the first stage, VR1 equals to VR2. Similarly, here also we'll take VR3 equals to VR4 and beta 3 equals to beta 4. For VR3 equals to VR4 and beta 3 equal to beta 4, I can write the above equation as W2 equals to, let us take the 2 times, both will be same, right? Both will be same. VR3 equals to VR4, both are same, and beta cos beta 3 equals to cos beta 4, both are same, right? So 2 times 2U by GC into VR3 cos beta 3. VR3 cos beta 3, right? Now here VR3 cos beta 3, is HI. It can also be written as HJ minus U. HJ minus U. HJ is V3 cos alpha 3, V3 cos alpha 3 minus U. V3 cos alpha 3 minus U. Look at the board carefully. W2 equals to 2 times U by GC into VR3 cos beta 3. VR3 cos beta 3 is HI. HI can be written as total length, total base minus U. Total base is V3 cos alpha 3. V3, sorry, V3 cos alpha 3 minus U. V3 cos alpha 3 minus U here, right? So, look at the board carefully. V3 is equals to V2. We assume that V3 equals to V2. V2 and V3 are same, and alpha 2 and alpha 3 are equal. Alpha 2 equals to alpha 3 and V2 equals to V3. So let us replace V3 by V2 and alpha 3 by alpha 2, right? Okay, look at the board carefully. W2 equals to 2 times is into, let me write V2 in place of V3 and cos alpha 2 in place of alpha 3 minus U as it is. Minus U as it is. Now, what is our main motive? What is our main motive? We have to write the final equation in terms of U V1 alpha 1. U V1 alpha 1, right? So still it is not in the final form. V2 alpha 2 is there. V2 cos alpha 2. So V2 cos alpha 2 means DE. V2 cos alpha 2 means this DE. This DE can also be written as VR2 cos beta 2 minus U. VR2 cos beta 2 minus U. Look at the board carefully. W2 equals to 2U by GC as it is into V2 cos alpha 2 is DE. This DE can be written as CE minus U. CE minus U. CE मान VR2 cos beta 2. Okay? ध्यान से सुनना. VR2 cos beta 2. VR2 cos beta 2 minus U this as it is. Okay? Minus U this as it is. Now look at the board carefully. W2 is equals to 2U by GC as it is. 2U by GC as it is into this VR2 cos beta 2 can be written as. Okay. Again here, VR2 equals to VR1 and beta 2 equals to beta 1. Beta 2 equals to beta 1 cube because the blades are equiangular. The blades are equiangular. Remember, for the fixed blades or the moving blades or the second set of moving blades, we are assuming beta 3 equals to beta 4, alpha 2 equals to alpha 3, and beta 1 equals to beta 2 for equiangular condition, right? So here I can assume VR2 equals to VR1 and beta 2 equals to beta 1. So let us write the same thing here. VR1 cos beta 1, VR1 cos beta 1 minus U minus 2U. Minus U minus 2U, right? Okay. Let me rewrite this equation here for there is a constraint in space. Okay, I have written the same here, same equation from the last step. W2 equals to 2U by GC into VR1 cos beta 1 minus 2U. Again, VR1 cos beta 1 is BC. VR1 cos beta 1 is BC. And this BC can also be written as BD minus U. BD minus U is a BC, right? So BD is how much? How to write BD? V1 cos alpha 1. V1 cos alpha 1 is a BD. So BD minus U. Ultimately, we have to write the final equation in terms of V1, U and alpha 1. Right? That is our main motive. Right? So W2 is equals to 2U by GC. 2U by GC into VR1 is V1 cos alpha 1 minus U. V1 cos alpha 1 minus U minus 2U as it is. Minus 2U as it is. So W2 can also be written as 2U by GC into V1 cos alpha 1 minus 3U. Minus 3U. Let me keep this as equation number 2. Let me keep this as equation number 2. To obtain the net work transfer from both the stages, just add the equation number 1 and 2. Just add equation number 1 and 2. Adding, let us add the equation number 1 and equation number 2. So therefore WT equals to W1 plus W2. WT equals to W1 plus W2. So WT equals to equation number 1 and equation number 2. Equation number 1 and equation number 2. Add both the equations, and out of these two equations, equation number 1 and equation number 2, 2U by GC is constant. 2U by GC is a common term. Let me take outside the bracket here. 2U by GC is common. 2U by GC. 2U by GC into what is the remaining term inside the bracket? V1 cos alpha 1 minus U. V1 cos alpha 1 minus U plus V1 cos alpha 1 minus 3U plus V1 cos alpha 1 minus 3U. V1 cos alpha 1 minus 3U, right? Now V1 cos alpha 1 is 2 V1 cos alpha 1, and minus U and minus 3U become minus 4U. Minus 4U. Okay. So WT equals to 2U by GC as it is. 2U by GC as it is into V1 cos alpha 1 and V1 cos alpha 1 is a 2 V1 cos alpha 1. 2 V1 cos alpha 1 minus U minus 3U. Minus U minus 3U is minus 4U. Minus 4U. Okay. So let us take 2 outside the bracket. 2 into 2, 4. So WT equals to, so take 2 outside the bracket. Then I can get 2 to the 4 here. 4U by GC into V1 cos alpha 1 minus, as we are taking 2 outside the bracket, so here it will become 2. 2U is remaining here. 2U is remaining. Okay. This is the work obtained, the total work obtained from both the stages. So now we have to divide this equation by total energy supplied to the blades, that is V1 square by 2GC, that is a kinetic energy, right? So to get the blade efficiency in terms of alpha V1 U, to get the blade efficiency in terms of alpha V1 and U. Okay, look at the board carefully. So W net or total work obtained is 4U by GC into V1 cos alpha 1 minus U, right? So keep it as equation number 3. Now, as per the definition of blade efficiency, how we can define? It is a total work obtained from the turbine to the energy supplied to the turbine. The blade efficiency is total work obtained from the turbine by the rotation of the blades or the runner to the total energy supplied to the runner or the blades, right? So blade efficiency, we know that blade efficiency neta B is total work done per kg of steam divided by energy supplied per kg of steam. energy supplied per kg of steel. So therefore, blade efficiency is given by total work done is WT divided by the energy supplied is. The energy supplied is purely in the form of kinetic energy, the high velocity jet of the steam, right? The high velocity steam jet. So it is written as V1 square by 2gc. V1 square by 2gc, right? So let us substitute the equation number 3 in this equation for the WT. So therefore, WT is 4u by gc, 4u by gc into V1 cos alpha 1, V1 cos alpha 1 minus 2u divided by V1 square by gc, V1 square by 2gc as it is. V1 square by 2gc as it is. Okay. So this GC will get cancelled. GC will get cancelled, and it will go to the numerator. It will go to the numerator. So therefore, blade efficiency is given by blade efficiency is given by take 2 outside the bracket. Here it will go to the numerator. So 8u by V1 square, 8u by V1 square into V1 cos alpha 1 minus 2u as it is. Okay. Now, let us open the bracket by multiplying u and V1 square. Let us open the bracket by multiplying u and V1 square. Look at the board carefully. So blade efficiency is given by this 8 as it is into u and V1 square. V1 and 1 V1 will get cancelled. So we'll get u by V1 into cos alpha 1 as it is minus u into u square, 2u square divided by V1 square as it is. So from the fundamentals, we know that the ratio of u by V1 is always 5. That is a speed ratio. But we know that u by V1, that is the ratio of tangential velocity of the blade to the absolute velocity of steam. The ratio of tangential velocity of the blade to the absolute velocity of steam is the speed ratio. Which is represented by phi. Phi is nothing but the speed ratio. Now let us use the phi in this equation. So I can write eta b equals to 8 as it is into u by v1 is 5 cos alpha 1 minus 2 into phi square. Right? 2 into phi square. Hope this is clear. Now, in order to get the condition for maximum blade efficiency, let us differentiate this equation with respect to phi and equate it to 0. Because the only variable is phi here. Alpha 1 is not a variable. Alpha is a fixed parameter. It is not variable. So in order to get the condition for maximum blade efficiency, we have to, let me keep it as equation number 4. Okay. Let me keep it as equation number 4. And let us differentiate this equation with respect to phi and equate it to 0 to get the condition for maximum blade efficiency. Okay. Let me write this equation number 4 on the top. Okay, so let us differentiate the equation number 4 with respect to phi to get the condition for maximum blade efficiency, right? So write down to get the condition for maximum blade efficiency, differentiate equation number 4 with respect to phi. Look at the board carefully. So differentiation of neta b with respect to phi and equate it to 0, right? Okay. Now the differentiation of this term, this complete term. So what I can write here? So differentiation of phi into cos alpha 1 is only phi here, only cos alpha 1, and the differentiation of 2 phi square is 4 phi, 4 phi minus 4 phi as it is, and of course here equal to 0. Okay, so I repeat it once again. Let us differentiate equation number 4 with respect to phi and equate it to 0. So the differentiation of phi cos alpha 1, as we are differentiating with respect to phi, right? So the cos alpha 1 is a constant term. The only variable is phi, right? So cos alpha 1, it remains as it is, minus, so 2 phi square. The differentiation of 2 phi square with respect to phi is 4 phi. 4 phi equal to 0 as it is, right? Okay, so therefore, here I can get phi equals to cos alpha 1 by 4. Cos alpha 1 by 4. So remember guys, to get the maximum blade efficiency, the speed ratio phi should be equals to cos alpha 1 by 4, right? Now to get the equation for maximum blade efficiency, let us resubstitute the specific speed, the speed ratio phi in equation number 4. Substituting the phi in equation number 4. Write down to get the maximum blade efficiency, use phi in equation 4, or substitute phi in equation number 4. So therefore equation number 4 will become maximum blade efficiency. Maximum blade efficiency into 8 as it is, 8 into phi is cos alpha 1 by 4. Cos alpha 1 by 4 into cos alpha 1. It is cos square alpha 1 by 4. Cos square alpha 1 by 4 minus, here 2 as it is, phi square is cos square alpha 1 divided by 16. 2 as it is into cos square alpha 1 divided by 4 4 is 16. 4 4 is 16. So 2 1s are 2 8s are 2 1s are 2 8s are. Okay. Now cos square alpha 1 by 4 and cos square alpha 1 by 8. So 1 by 4 minus 1 by 8. Okay. On simplification, I have taken 1 by 4 outside the bracket, right? So here we are left with cos square alpha 1 minus cos square alpha 1 by 2. So 1 minus half, that is half. So 2 will get cancelled. Ultimately, we are left with cos square alpha 1. Cos square alpha 1. So this is the equation for maximum blade efficiency of a two-stage impulse turbine. So you have to remember the condition is phi equals to cos alpha 1 by 4, whereas the maximum blade efficiency equation is neta b max equals to cos square alpha 1. That is neta b max equals to cos square alpha 1. Cos square alpha 1. This is the required equation. Okay. So this is very important derivation from your examination point of view. Okay. Further, if you have any doubts regarding the problems, notes, numericals, previous year question papers, here is my WhatsApp number. You can contact me. That is 9886539074988653907. And if you like this channel, then don't forget to share and subscribe my channel. Right? My channel name is Thermal Engineering Manoj Shendre. My channel name is Thermal Engineering Manoj Shendre. Thermal Engineering Manoj Shendre. So do like, share and subscribe my channel. Have a wonderful day. Goodbye. Take care.